Hey there, and welcome back to the 2016 Practice Calculus AB examination. We already did problems 1 through 10, and in this video, we are going to do problems 11 through 20. I feel good. I feel good. I think this is going to be a great little video. I'm already feeling it this morning. Who knows? But you know you're going to like the video. Like it now. Follow me, because how else are you going to get notified when I put up the next video for problems 21 through, I don't know what it is, 28, 30, whatever, unless you follow me. So when I put up those videos, you get a notification and like it, because like I said, that really helps me. Let's get started, man. I'm feeling this. I'm feeling this. Number 11 says the graph of function f is shown in the figure above. Which of the following could be the graph of f prime? All right, f prime, which is the derivative of f. This is the graph of f. Let's be perfectly clear. One of these down below is the graph of the derivative, okay? I think there's 5 choices here, okay? So first thing, I always tell my students, it's critical that you understand, all right, what you have when it comes to a graph and what you need. All right, so I am just going to kind of mimic the graph next to me. Here's my x, here's my y. However, on this graph, my y is going to represent the derivative of f. Derivative is the same thing as slope. Okay, that is so crucial to know. The first thing I'm going to do is I'm going to see on my original graph, where do I have a slope of 0? At this point, my derivative is 0, and at this point my derivative is 0. Okay, so this x value and this x value, I don't know where they are, just approximately it looks like it's probably right here and right here. Okay, remember, my derivative is what the y value is. If I have a y value of 0, that's an x-intercept. It should be touching the x-axis. Okay, y is 0 here, right? And then above the x-axis are all positive values for y, which means I should have positive slopes. Below my x value are all, below my x-axis are all negative y values. So that's where my negative derivatives will be, okay? So let's look at our original graph, and let's start in between our zeros, all right? This line right here is a positive slope. That is going up. That means any graph I draw on my derivative graph should have positive y values. Starts at 0 as positive, then comes back to 0. Remember, we started at 0, positive, then went back to 0. That's exactly what I did on my derivative graph. Now let's look outside my zeros on my original graph. To the right, this is a negative slope, which means I should have a negative derivative. If I have a negative derivative, I need negative y values. So I should be down here. Okay? Those are all negative y values. Okay? Same thing with the left side of my original graph. This is a downward or negative slope, which means anything to the left of my left 0, okay, should be negative. I want negative derivatives, want negative y's. That's what the graph of the derivative of f should look like. And if I scroll down here, that looks just like choice B. Right there, a downward parabola. Okay, that's it, right there. Don't get confused when you go back and forth between the original graph and the derivative, okay? Maintain your patience and know that you understand it. Number 12, if C is a value in between 0 and 1, okay, C is greater than 0 and C is less than 1, okay, what is the area of the region? That screams to me integral, okay, integration. The area of the region enclosed by the graphs y equals 0, y equals 1 over x, x equals c and x equals 1. Well, here's my x-axis, here's my y-axis. Let's do this. First, for y equals 0, well, that's the x-axis. Y equals 0. Next, y equals, we'll do this in different colors. Y equals 1 over x probably looks something kind of like this. That's y equals 1 over x. All right? X equals 1. I don't know. Let's say 1 is right here. That's x equals 1. Now, for c, I know one thing. C is between 0 and 1. If 0 is right here and 1 is right here, I mean, C can be to some point in between, right there. X equals C. They want the area of this shape right here. Okay? So I'm going to integrate that. I'm going to integrate from my lower bound, C, to my upper bound, 1, my function. You always need dx. Now, this is multiple choice, so you don't have to show, like, appropriate work or whatever, but I'm showing you as if this were a short answer problem. All right? And we don't get a calculator. So, rules for derivatives, you better remember them. The derivative of ln of x is 1 over x. So if I have 1 over x and I want to go backwards, that just gives me the ln of x. I don't have to do plus a constant. How come? Because I have bounds. Okay? The ln of x, I want that from 1 to c. All right? So I take the ln of 1 minus the ln of c. Resist the urge, not because you're wrong, but because the way our multiple choice answers are presented. This does equal 0. So you want to say the negation of ln of c should be the answer. Okay? I don't see that. I see positive ln of c. So a lot of students, well, some of my students will say, oh, maybe I made a mistake. Maybe it shouldn't be negative. Maybe it should be positive. No, 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 no. I'm going to bring you back to Algebra 2 when life was easy. I don't know if you touched on this in pre-calculus or not, but our rules for expanding logs and natural logs or contracting them, bringing them, shrinking them together. If I'm subtracting two separate natural logs, I can make it into one with a division or fraction, numerator over denominator. Okay, the ln of 1 over c. And now it becomes a lot more clear what the answer is. It's not choice C, it is choice B. So number 13, you're going to play with my heart like this, huh? The derivative of the inverse of tan plus 2 times the square root of x. First off, I'm going to rewrite this. Whenever I'm taking derivatives, I love to have exponents. That is x to the 1/2. Okay? 2 times x to the 1/2. The square root of x is equal to x to the 1/2. You need to remember your rule for the derivative of inverse tan. It is 1 over 1 plus whatever is here squared. So that's x squared. Right? Plus the derivative of 2x to the 1/2. The exponent comes down, and I multiply a half times 2. That just gives me 1. Okay? I have my 1x, but then I got to subtract 1 from the exponent. If I have a half, I subtract 1, it becomes negative 1/2. All right, well, it looks like the radicals are back in the answer, and it looks like there's no negative exponents. So what I'm going to do, I put this over 1. I got to flip this to make that exponent positive. I now have 1 over 1 plus x squared plus 1 over x to the positive 1/2. All right? And again, I want to convert that exponent back to a radical. This is really going to convert to the square root of x. Can't do anything further. Choice E. 14. 14 is kind of I mean, it's not tough when you understand it, but we really don't get questions like this asked in this manner, okay? If y equals f of x, and that's a solution to the differential equation dy dx equals e to the x squared with the initial condition f of 0 equals 2, which of the following is true? Okay, so if I solve this with this initial condition, okay, I always train my students to think of that as a coordinate, okay? The solution should be this. All right. So obviously, all of our answers are f of x equals. So I'm really just trying to find this right here. When I first did this, I wanted to make this separable differential equations, meaning I'd multiply both sides by dx, and I would get e to the x squared dx dy on this side. I would integrate both. But even if I did u sub, this becomes a bear to integrate. Okay, it becomes a bear to integrate. And what do I mean? Even if I made this e to the u, and u was x squared, du would be 2x dx. I multiply both sides by a half, so get rid of this. I don't have, once this goes bye-bye, I don't have an x dx to sub out. I just have the dx. So I'm not going to use separable differential equations. And trust me, when I first did this, that was the first way I actually tried to solve this. And then I started to look at this, and I looked at the answers. Some of these answers are written in integral form, meaning they're kind of set up without being solved. And that's what I started to focus on, and that's going to make this a lot easier. Okay? If I solve this and go backward to get y, okay, that means we're going to go backward from the derivative. That means I need to integrate. Okay, well, let's integrate this. All right? I'm going to integrate that. So my y, or my f of x, is going to equal, it's a solution to this. Okay? But what about that 0 and 2? Okay? This means when we start at 0, that's when we start, I already have an output of 2. So this just tells me that when I start, I already have a value of 2. Okay, let's put this in context. Let's say this represents gallons per minute, and I want to go backward to gallons. Okay? When I start, I already have 2 gallons in the tank before I start adding all that rate. Okay? I start adding. So that's an initial value. I got to look at that not as a coordinate, but as a condition, meaning I already have 2 into whatever I'm going to have when I integrate here. Let's say for conversation's sake, okay, let's say for conversation's sake, this gives me a value of like 12, whatever. I need to add 2 to it because I had 2 to start before I even did the integral, right? So it's not A, it's not B. I need an integral. C does not have the 2 plus. Okay, so now I'm looking at the difference here. Okay. From the beginning, I have 2. That means my lower bound has to be the beginning. I have to start at 0, because before 0, I already had 2 in there. And then I go up to some value x. I want the one with the 0 on the bottom, not the 2 on the bottom. The answer is choice D. Now, they're going to say, let's make this a t. Okay? Because remember, when I take the derivative of this, when I go back here to get rid of the integral, the x will replace the t. Okay? So that type of mindset, it's not typical for this problem. Normally, they'll ask you to integrate something. Maybe you have feet per second. Well, how many feet did you travel? Oh, and by the way, at time 0, we already had 8 feet out, so you need to add 8 feet. That's what that initial condition is. Normally, it's asked in the scenario that I just gave you. There is some sort of label. Gallons per minute. Feet per second. There's some sort of label there. Here, there's not, so it's weird. You always want to do the separable differential equations, but you definitely don't have to. And how do you know? The way those responses are framed, all right? Again, that was a tricky one. And almost right on cue, we have problem 15. The function f of t gives the rate of evaporation of water in liters per hour. We were just talking about some sort of measurement per time. Okay, from a pond where t is measured in hours since noon, which of the following gives the meaning of the integral from 4 to 10 of f of t in the context described? So, if I have f of t, and f of t is already a rate, it's in liters per hour. So, if I have liters per hour, and I take the derivative of that, that's liters per hour squared. If I go backward, okay, and I take the integral, which is what we have here, that turns the rate into the unit. That is just liters. So when I integrate this, I'm going to end up with something which is representative of liters. Okay? Okay. So that's the first thing we need. I'm going to write that down. All right, it's going to be liters. Okay, that's a check. Boom. The next thing is, t is measured in what hour since 12? So we're going to start from 4 to 10. But 4 to 10, okay, are the hours since noon. 4 hours from noon is 4 p.m. 10 hours from noon is 10 p.m. So in the context of this problem, this is evaporation in liters per hour. So I guess we're going to talk about the liters evaporated from 4 to 10 p.m. Okay, and look at choice B, the total volume of water in liters that evaporated from the pond between 4 and 10 p.m. Boom. That's just an interpretation problem. No math needed whatsoever. Or I really should say no calculations needed whatsoever. Number 16. Oh, good, a good old-fashioned just derivative problem. The first derivative of the function of f is given by f prime of x equals 3x to the fourth minus 12x cubed. What are the x coordinates of the points of inflection of the graph of f? Anytime they ask me for points of inflection, okay, that's the second derivative. Not only is it the second derivative, but the second derivative is 0, but around that 0, my second derivative should change, either positive to negative or negative to positive. There has to be a change around here, but first, that change can only happen when the second derivative is 0 or undefined. But you're going to see that our second derivative will never be undefined once we figure out the equation for the second derivative. All right? So let's start with that. Second derivative of x, f of x, is, that becomes 12x cubed minus 36x squared. Set that equal to 0. Factoring never goes away. I tell that to my Algebra 2 kids, I tell that to my pre-calc kids, and I tell that to my AP Calculus kids. Let's factor out a 12 and then x squared. Okay? That leaves us with x minus 3. Okay. I'm going to take both of these, set them equal to 0. X would be x minus 3 equals 0, so x would equal 3. Okay? 12x squared equals 0, so x would equal positive and negative 0, or we could just say 0 in this case. Okay? So x equals 0 and x equals 3. Let's create a number line, my friends. My little Irish friends, let's create a number line. Here's 0, here's 3. This is my x value. These are the 2 points where my second derivative is actually 0. I need to check values in between those zeros and put them in the second derivative. Okay, I can put them in the second derivative here, right into the equation, or I can plug them into this and figure it out, because that is the factored form of the second derivative. And I want to see, are they going to change from positive to negative or negative to positive? Let's figure out, okay, let's pick 1. That's an easy one to pick. We'll pick 4, and we'll pick negative 1. All right? So let's start with 4. If I put a 4 in here, okay, anything that this parenthesis has will always be positive. Okay? So let me do this here. I got 12x squared times x minus 3. Okay? Anything I put here, if I square it, will be positive. A positive times 12 will always be positive. This will always be positive, this. Okay. But what happens if I put a 4 here? 4 minus 3 is 1. A positive 1 times a positive value will still give me a positive 1. So this is going to be positive here. Okay? Let's try the number 1. Again, this is always positive. But what happens if I put a 1 here for this 3? I get negative 2 now. A negative number times a positive number will indeed give me negative. So right here, it's negative. I got to try one more thing, and I'm going to try negative 1 this time. Okay? Again, this will always be positive, this parenthesis. If I throw a negative 1 in here, minus 3, I now have a negative 4. A negative number times a positive number will also be negative. So I've got a downward frown, or it's concave down. An inflection point, well, actually, where the second derivative is 0, but then it continues to be sad, and then it gets happy here. So at this point, at 3, that's an inflection point. That's where I change from negative to positive. All right? So only at 3, which I believe is choice A, and there you go. Number 17. Let f be the function defined by f of x equals 1 over x. What is the average value of f on the interval from 4 to 6? Now, average value, okay, average value. Whenever they ask for average value, okay, we're going to integrate because we're going to take all the values, but then whatever my upper and lower bound is, I'm going to have to multiply by 1 over the upper bound minus the lower bound. Right? I got to average it out. Okay, so I'm going to have to multiply by 1 over the difference in bounds. My bounds are right here. A will be 4 and B will be 6. I'm going to integrate this from 4 to 6. Okay, and over that span of 2 units, don't I gotta, like if I'm trying to average 2 tests, don't I add up the test scores and divide by 2? This is like adding up the test scores because I'm adding up all that area under the curve. And if I multiply, okay, by 1 over 2, this really ends up being 2. Isn't that like dividing by 2? It is. Okay, so you just got to realize that. Boom. For problem number 12, we actually integrated this. That's the ln of x, all right? And we want that from 4 to 6. And oh, by the way, I'm multiplying it by 1 over 2 because 6 minus 4 gives me my 2. All right? So let's do this. We have 1/2 times the ln of 6 minus the ln of 4. This is separate. Okay? And if I want, I'm taking a look here. Again, that rule comes back into play. These are going to come into one natural log function. Numerator, denominator, times 1/2. Well, that can be reduced. 1/2 times the ln of 3 over 2. 6 over 4 reduces to 3/2. And that's choice C. That wasn't terribly difficult at all. You just need to know your rules. And you need to know that average value means take the integral and multiply it by 1 over the difference of your bounds. Number 18, the points 3, 0. Okay, let's highlight this. Boom. The points 3, 0, boom, right there. X 0, which is this, x, comma, 1 over x squared, which is here, and 3, comma, 1 over x squared. Believe it or not, this is this right here. How do I know that? Because if this y value here is 1 over x squared, it's the same y value when x is 3. So this will be 3, comma, 1 over x squared. All right? There we go. Are vertices of a rectangle where x is greater than or equal to 3. X has to be greater than 3. It's to the right of 3 on the x-axis, okay? As shown in the figure above, for what value of x does the rectangle have a maximum? Mins and maxes are first derivative, okay? And again, I want to find the max point, which means I need a critical point, figure out where that's 0. And I want to have a positive slope and a negative slope around that point where we have a 0 for the first derivative. That is essentially what we're going to do. The problem is we don't have an equation to take the first derivative of. Maximum area. What is the area of a rectangle? It's length times width, okay? My length is this right here, from 3, okay, to whatever x is. All right? 3 to whatever x is. So let's do this. How do I figure out what that is? Well, let's go here. If the point from here to here is x, I want to subtract from here to here 3 because I truly want this distance. Okay, so I take x and subtract the 3. So that is x minus 3. Okay? Okay, and this distance is just the y value. 1 over x squared. Bam. All right. So, plenty of ways to do this. This is the area of the rectangle. And I want the derivative. Okay, well, let's take the derivative of that. I could just do the product rule right there. I'm going to distribute that 1 over x squared to make it a little bit easier for me. I don't know. I'd like to. So, and I'm going to make it into a polynomial. So I've got x over x squared minus 3 over x squared. Really, at this point, I could have done the product rule with the quotient rule for this. In between. I could have brought that x to the negative 2 up, or excuse me, x to the 2 up, make it x to the negative 2, and take the derivative that way, which is almost what I'm going to do right here. Okay, but there's plenty of ways to take the derivative. All right, so I'm going to reduce these. Okay, that ends up with 1 over x, because this reduces 1x, cancels with one of these x's. And I'm going to bring, well, this one I really can't do anything with. All right, so what I can do, in fact, I haven't even taken the derivative yet. Okay, let me take that. I can take a 1 out of x out. That would be 1 minus 3 over x. Am I doing that right? I am. Okay, and I could take the derivative at that point. Although I think I'd like to keep it squared, so that would always be positive on the outside. I could do that. I could do that. I sure could. All right, let's do that. In fact, for the sake of ease, I'm looking at this. What I'm going to do is, and I apologize if you write in pen, okay, I'm just going to bring this 2 up at this point. I'm going to say 1 over x minus 3x to the negative 2. Because I have a polynomial here, right here, let's just take the derivative of this, okay? The derivative of this, if you do low d high, high d low, or in fact, I can make that. Man, look at me go. This is the problem when your brain is constantly working. You want to bring this up and call this x to the negative 1. All right? So now, let's take the derivative of these. Exponent comes down, it's negative 1x to the negative 2, because I got to subtract 1 from it. Okay? Minus, okay, this comes down, negative 2 times 3 is positive 6, x to the negative 3. All right. All right. Now, at this point, I think factoring is going to be easier. I was looking at all the different ways we could do this, and I was trying to go through that and think of the easiest way. To me, this is it. It might not be to you. Again, at this point, if you want to take the derivative a different way, you're fine. Make sure you come up with the same answer, and if not, try and follow what I'm doing here. Let's take out an x to the negative 2. That leaves me negative 1, okay? And this ends up being plus 6x to the negative 1. All right, that's my derivative. And let's clean it up. Okay, if I'm going to have to put in numbers, I'm going to have to set this equal to 0. I'm going to have to see where, where it's positive or negative. I'm going to make this 1 over x squared. And then we have negative 1 plus 6 over x. Okay, this is my second derivative, the first derivative. Sorry. Man, it's thrown me for a curveball. All the numbers and all the derivatives I could take. But here, let me focus on this one, okay? Where's this equal to 0? The only place this is equal to 0 is when this parenthesis is equal to 0. This will never be 0. I can never have 0 on the bottom, okay? You can never have 0 on the bottom, all right? So this is equal to 0 when x is 6, all right? Because negative 1 plus a positive 1 gives me 0. And the only way that this fraction is positive 1 is when x equals 6. Okay, so let's go to our number line. Whew, here's where x equals 6. That's where the first derivative is 0. All right? Now remember, I want this to be a maximum point. I want this to be maximum point. Remember, maximum area means maximum point, which means I got to go positive to negative. Okay? I want this side to be positive and this side to be negative. So let's plug some numbers in, shall we? Let's plug 5 and 7. Okay? And I'm going to plug those into 1 over x squared times negative 1 plus 6 over x. This will always be positive. I'm multiplying a positive times whatever this is. If I throw a 5 in for this x, I'll get 1 and 1/5. Okay? If I take a negative 1 from that, it will still stay positive. Okay? Positive slope. Good. I want it to be positive anyways. Positive slope here. Let's throw a 7 in now. If I throw a 7 in for this x, that will be 6/7. Literally, it's less than 1. If I have a negative 1 and I add 6/7 to it, I'll have a negative 1/7. A positive times a negative gives me a negative. Good. The maximum occurs at x equals 6. Whew! Wow. Man, my brain started drifting into all the possibilities. Then I was trying to check all the possibilities to see if my work would end up being right. And I was doing multiple problems in my head, which is none of your problem whatsoever. But now guess what? 18 isn't your problem as well, because the answer is C, and it's 6. Please, please, please don't fall into this trap. What are the values of x for which the integral from x to 2 of t cubed dt is equal to 0? Don't think that, oh, look at, we have a variable on the bottom, and I'm going to put the x in for the t by taking the derivative. It's not telling you to take the derivative of this. Okay? It really wants you to integrate that. Okay? The integration to this is I add 1 to the exponent, and then I divide by that new exponent. I want that from a lower bound of x to an upper bound of 2. And by the way, that should equal 0. All right, so let's plug in our numbers. 2 to the power of 4 over 4 minus x to the power of 4 over 4 equals 0. All right. Okay. So, I mean, I can multiply anything by 4. This is going to be 16 over 4 minus x to the 4 over 4 should equal 0. 16 over 4 is just like saying 4 minus x to the 4 over 4 equals 0. Let's add this to both sides. So I got 4 equals x to the 4th over 4. Okay, it's good. Let's multiply both sides by 4. I now have 16 equals x to the 4th. And if I take the 4th root to make this x, 2. But guess what? Both of those work because I have an even exponent. So it will always turn out to be even. Okay, it's positive and negative 2, which is choice D. And I felt like I went through that fast after that last problem, 18, but there it is. Don't just try and take the derivative of my integral because I have one variable in one of the bounds and a different variable into the function I'm integrating, okay? You only do that if it tells you to take the derivative of this, or they write it as the derivative of the integral. Can you believe it? We're almost done. And this is going to be a little bit of a lengthy problem. Let h be the function defined by h of x equals the integration from x to pi over 4, as the lower bound, and x to the upper, of sine squared of t dt. Okay, which of the following is the equation of the tangent line to the graph of h at the point where x equals pi over 4? Y minus y1 equals derivative or slope times x minus x1. I already have x1. So that's x minus pi over 4. Okay. How do I get x when I have y? Well, I go to the original equation. That's like y equals. So the integral from pi over 4 to x. And what's x? Pi over 4 of the sine squared of t dt. All right. By the way, anytime the bounds are the same, the answer is always 0. Okay, so y equals 0. That was nice. Y minus, there's my 0. I need the derivative. I need the what? I need the derivative of my equation at this. My equation is this. Now I need the derivative of this. Now I'm being told, if you know what you're doing, that slope is derivative, that I need the derivative of the integral of x to pi over 4 of sine squared of t dt. Now, the derivative and integral go bye-bye, and the x goes in for my t. So it's sine squared of x. Okay? At what value of x? When x is pi over 4. That is 45 degrees. Oops, I don't know why I'm drawing a percent sign. So let's take the sine of 45 and square it. The sine of 45 is 1 over radical 2. If you don't know your special triangles, you should know them. It's 1 radical 2. Okay? The sine of this is opposite over hypotenuse. So it's 1 over radical 2, and I got to square the whole thing. 1 squared is 1. If I square radical 2, it's 2. That's your slope. 1/2. All right, so y minus 0 is just y equals 1/2 times x minus pi over 4. Looks like my answer is D. We are done. That wasn't too bad. That wasn't too bad. 39 minutes, though. Like this video. My God, I just spent 40 minutes with you. Follow me so you are alerted of when I continue these, and you will be notified when the next videos come out. I love you guys for hanging with me through this. I'll see you for the next video.